In this video, we start part 2 of Unit 3 with our exponential and logarithms. To begin this week, I wanted to share with you a summary chart. This would be a good chart or good piece of reference for use in the future when solving logarithmic equations or exponential equations. Some things to keep in mind here is first that in all of these um, properties and formulas, A, B, M, and N are numbers. They're not variables. And A and B are going to act as the base values of our logarithm, so they must be positive and not equal to 1. And in order to comply with the domain of logarithmic functions, we're going to say that M and N are both positive as well. One formula that we didn't spend any time talking about last week is this change of base formula. And this is particularly helpful if you're using a calculator that does not have a logarithmic key that allows you to input the base of the logarithm. Some calculators don't have a key that will allow you to do that, and when you press the logarithm key, all that you get is a logarithm with a base of 10. So if you are working with a calculator that has a simple logarithm key, or if you're using your cell phone calculator that has a log key, I'll show you how to complete a complex logarithm even with a simple logarithm key. Now, before we get into any examples for today, I have 3 quick true-false questions to see if you recall the properties of logarithms when it comes to expanding or condensing them. Is it true or false that the natural log of x plus 3 minus the natural log of 2x is the same as the quotient of the natural log of x plus 3 divided by the natural log of 2x? If it's false, please explain what the correct solution should be. Pause the video and try this now. Well, we do have a quotient rule that allows us to expand or contract logarithms, but what we have to recognize is that when we're subtracting 2 logarithms with the same base, we can condense them into a single logarithm where the arguments are divided. So I don't want 2 logarithms here inside of a quotient. What I really want is a single logarithm with a quotient of our 2 arguments. That would be appropriate. What about the second one? Was our power rule used correctly for this logarithm? Pause the video now and try this one on your own. Well, this one is also false. It looks like the exponent was brought down to the front, and that's a good thought, but the problem here is that this exponent really is only affecting the x component right now. This exponent of 4 is not a part of the number 3. So had this exponent been here on the outside of the grouping symbol, then we would have been okay. This 4 could then be brought down. We'd have 4 times log base 2 of 3x. However, what really should have happened here in terms of expanding is that we should have separated at this multiplication sign first. Log base 2 of 3 plus log base 2 of x to the 4th power. And then we could remove or bring down this exponent of 4 to the front after after this exponent of 4 has been identified as affecting only the argument of the logarithm. So we could say log base 2 of 3 plus 4 times log base 2 of x. Now here again, this may be beneficial. This sort of process may be beneficial because if we pretend that this was equal to some number, I'm just making up a value 10 here, we're getting closer and closer to being able to isolate the number x. In fact, this log base 2 of 3, that's just going to calculate out to be some number. We could subtract that from both sides to move it over to the right here. We could then divide by 4, and then we'd be left with an expression involving x that we could rewrite as an exponential and solve for x then as well. So the reason for this expansion and for combining logarithms makes it simpler for us to solve equations on a larger scale. And for this last example, I think a good argument for this is to use the change of base formula. So let me just point that out to you. This is going to be a false statement, and I'll explain why. The change of base formula says that if I have two logarithms with the same base, and we are creating a fraction out of that, what I can end up doing is creating a single logarithm with a different base. Notice the base value was b in this quotient here on the right, and the base value over here ends up being a. Well, the base of the new logarithm ends up being the argument of the logarithm in the denominator, and the argument of the new logarithm was the argument of the numerator's logarithm just a moment ago. So essentially, we can eliminate or disrupt this base value of the logarithm if we needed to change it, and focus solely on the arguments of the logarithms in order to rewrite. Now we have that over here too. The base of these logarithms is technically the number e. We don't have it written because we're using the natural logarithm notation. But we do have two logarithms with the same base, and the arguments of each are different. So this natural log of 8 divided by the natural log of 4 is really just an exercise in the change of base formula. And this could be rewritten as log base 4 of 8. And so now that we know that log base 4 of 8 is another way to rewrite this fraction, let's ignore that for just a second. And the question was asking if this was equal to 2. Well, that would only be equal to 2 if 4 to the second power equals 8. And is that true? Is that true that 4 squared equals 8? And the answer, of course, is no. 4 squared is 16. It's 4 times 2 that equals 8. And the next 8 questions are meant to test your understanding of the log properties as well. We introduced these last week, so let's real quickly go through their solutions. When the base of the logarithm and the base of the exponent being evaluated in the logarithm match, then we can pretty easily answer this problem. We know the end result is going to be that exponent. Logarithms and exponents are inverses, so essentially this logarithm and this base cancel each other out, and we're left with, obviously, 71. For number 17, we see the same thing. The base of the exponent and the logarithm will cancel, and this will be equal to 7. We have negative 13. And for number 18, don't forget that e is a number and the natural log requires the base of e, so this expression is going to be equal to 8. The natural log's base is e with an exponent's base of e, so this result is negative 4. I'm going to jump over to number 16. Number 16, again, base of e, so this is going to simplify to the square root of 2. Now, that may seem mundane and mindless to do problems like that, those 6 there, but again, this is our way of stressing the importance of recognizing these formats to problems if we see them in a larger context. For number 19, let's condense this logarithm. Log base 8 of 2, I don't know what that is, and log base 8 of 4, I don't really know what that is, but since the bases are the same, we can condense this logarithm into log base 8 of 2 times 4. Lo and behold, we've got log base 8 of 8 and log base 8 of 8. Well, those two essentially cancel, and we know the result is 1. 8 to the first power is equal to 8. And so while we didn't know what log base 8 of 2 was, and we didn't know what log base 8 of 4 was, and to be honest, those are going to be some strange decimals most likely, what we do know is that the sum of those two is equal to 1. And we got that by using our log properties. Similarly with number 20, I don't know what log base 6 of 9 is. I couldn't tell you what that or this term is equal to, but by condensing them into log base 6 of 9 times 4, because of the sum of two logarithms is the same as the product of their arguments, we now have log base 6 of 36, and that's equal to 2. I know that that's equal to 2 because 6 squared equals 36. At this point, hopefully you are starting to do some of these logarithms mentally now, and you can answer some of the more simple ones, especially those with small whole number answers. So here again, we didn't know what log base 6 of 9 or log base 6 of 4 was, but the sum of those two terms is equal to 2. So let's think a little bit about questions 30 through 32. In the instructions, we're told that the natural log of 2 is equal to some number that we call a, and the natural log of 3 is equal to some number of b. So can we use that knowledge to rewrite each of these logarithms in terms of a and b? Can we solve, 29 through 32, can we solve 29 through 32 in such a way that our answers contain only a and b? Well, I would argue yes, we could. For example, in number 29, if I say that the natural log of 6 is equal to the natural log of 3 times 2, if we recognize that, then we might also recognize that we can expand this to the natural log of 3 plus the natural log of 2. And we said that the natural log of 3 was b, and the natural log of 2 was a. And we could say that the natural log of 6 is equal to b plus a, or of course a plus b, because order doesn't matter with addition. In number 30, we need to recognize that the quotient inside the logarithm's argument can produce two logarithms, the natural log of 2 divided by the natural log of 3. This time order matters though. Oops, sorry, I'm misusing that rule here. Order does matter, let me reiterate that, but it's not going to create a quotient of logarithms. Instead, it creates a difference of logarithms. And again, order matters because we have to start from the top and work our way down. So we want the natural log of 2 minus the natural log of 3, which in this case is a minus b. It could not be b minus a. For number 31 and 32, get creative here. Think of different ways that we can use the number 2 and 3 to recreate the number 1.5 and 0.5. Pause the video now to rewrite these and solve in terms of a and b. Resume playback in a moment to check your work. For number 31, I think it was pretty clear to see that 1.5 is the same as 3 over 2. So if the natural log is being evaluated at the fraction 3 over 2, we can split that into the difference of two logarithms, natural log of 3 minus the natural log of 2, which was defined as b minus a in our given information. For number 32, I was a bit misleading in saying that you had to use 3 and 2. We could use 1 and 2 in this case, because the natural log of 1, or any logarithm of 1, always equals 0. That's a property that we had learned before, and I believe it's in this list. Yep, there it is. Any logarithm with a base evaluated at 1 is always equal to 0. And so 0 minus a, of course, is negative a. If you were real creative, you could have written natural log of 3 divided by 3 times 2. That's natural log of 3 divided by 6. That's the same as 1/2. And you could have created the natural log of 3 minus the natural log of 3 times 2, which would have been, of course, natural log of 3 minus the natural log of 3 plus natural log of 2. And so we now have a b value minus b plus a. Notice the grouping symbol here had to be maintained because we were subtracting the natural log of 3 times 2, which means we're subtracting both natural log of 3 and the natural log of 2. B minus b, of course, reduces to 0, and when we're subtracting the a value, we get negative a as well. In either event or either approach, we obtain the same result. And so I'd like to challenge you right now. There are two logarithmic equations that you can solve before we get into our applications for this video. I'd like for you to pause the video and try solving these now. Make sure you put in an honest effort here. Consider the properties that are stated above and some of the practice problems that we've completed recently and that you've seen in Math Excel. What would it take to solve for x? Solve for x. In other words, give me the solution. What is x equal to? And better yet, can you do this without a calculator? I think both can be done without a calculator. So pause the video now and resume playback in a moment to check your work. And here we go. In this first example on the left, I used the power rule and I brought this exponent of 2 back in with x squared. So log base 5 of x squared equals log base 5 of 9. When the two logarithmic bases match, then I know the arguments match as well, and x squared must be equal to 9. If x squared was equal to 9, then x itself had to be either 3 or negative 3. But of course, we throw out the negative 3 because if negative 3 were to represent x, then we would have a problem here. The argument inside of a logarithm cannot be negative, so we can't evaluate log base 5 at negative 3. That doesn't exist. It's an extraneous solution. 3 is the only solution. On this side here, I was able to condense the two logarithms into a single logarithm by finding the product of these two arguments, x plus 6 times x plus 2. Now that I have a logarithm equal to 1, there are really two different approaches here. I chose to follow the loop rule. 5 to the first power must equal this. Or you might recognize that the logarithm with a base that equals 1 must also be evaluated at that base in order to equal 1. So in other words, we could have recognized the property that said that log base 5 of 5 equals 1. So therefore, x plus 6 times x plus 2 must be 5. In either case, we would have ended up with this phrase here. We'd have a quadratic equal to the number 5. And to solve the quadratic, we subtracted 5 from both sides. And then we had to solve this one. I solved it by factoring and found that x had to be either negative 7 or negative 1, but only negative 1 is acceptable. Now remember, x by itself is not being used as an argument here, but x plus 2 and x plus 6 is. So when x is equal to negative 1, we have negative 1 plus 2, which is a positive number. And when we have negative 1 plus 6, that's also a positive number. In both cases, when x is equal to negative 1, the argument is positive. However, if I use the number negative 7 and think negative 7 plus 6, well, that's a negative number. And negative 7 plus 2, that's also a negative number. And in both cases, that would be a problem. We wouldn't be able to evaluate the logarithm at a negative number. So because of that, we threw out the answer choice of negative 7. It's what we call an extraneous solution. So let's finish out this video with a word problem, or two. I think we'll skip the investment questions at the bottom of this handout in order to keep this video a little bit shorter. And in this population model, we'll only complete part A. Part B would be done much the same way. In part A, we're told that the population of the United States was 309 million and growing at a rate of 0.9% per year. And so when given that information, we can assume that the population follows the law of uninhibited growth, which is represented here. And the question becomes, when will the population be 419 million? And as part of your understanding of function notation, you need to recognize that this 419 is not being substituted in place of t. It's being substituted in place of the function notation, p of t. The population based on some amount of time is going to be 419. So if 419 equals 309 times 1.009 to the t minus 2010 power, then by using our log properties, we should be able to isolate t. Now, if our job is to isolate t or to solve for t, we have to work backwards through the order of operations, and I'm going to divide by 309 first. I would really like to add 2010 to both sides of the equation because that would come first in the reverse order of operations, but in essence, that's kind of protected by this grouping symbol that's keeping this expression in the exponent. So we can't do any work inside of the innermost parentheses until we finish everything else in that reverse order. So I am going to divide both sides by 309. Now, I'm also not going to use a calculator until the very last step. This will preserve accuracy, and it'll also illustrate how we can do this problem without a calculator if it were to show up on a no calculator portion of the test. Okay, so now I've divided both sides by 309, and I have essentially an exponential expression or equation. The base of the exponent is here, the power of the exponent is here, and the result of the exponent is over here. So if I have a base to a power equals some number, well, now I can rewrite as a logarithm. And rewriting as a logarithm is especially helpful since we're solving for t, which is stuck in the exponent. A logarithm will help us get after that. So I know the base of the logarithm must be the same as the base of the exponent. So this base 1.009 becomes the base of the log. And instead of evaluating the exponent at t minus 2010, we're going to evaluate the logarithm at the other value, which is 419 over 309. I don't know if that can be reduced as a fraction at all, but to be perfectly honest, I'm not that interested in it, because I can still isolate the variable t in this final step by adding 2010 to both sides. And I have a good solution here. This is a precise answer that would represent the time in which the population will reach 419 million. And I haven't even used a calculator at this point. However, if I do want the t value in terms of some decimal or a fairly precise answer, or approximate answer technically, then now I can go to the calculator and I can evaluate this expression. So I'll reach for a calculator and I'll turn it on. I'll press the on button until I get to this home page, and I'll choose a new calculator. We'll create a calculator page, and what I need is a logarithm, base 1.0, base of 1.009, being evaluated at the fraction of 419 over 309, and to that we will add 2010. I don't know if the calculator is going to give me a decimal or not, so to be safe, I'm going to press Control Enter so that I do get a decimal. And evidently in the year 2043, towards the very end of 2043 or almost 2044, that's when the population will reach 419 million. Since I like the decimal place, or I like 4 decimal places for accuracy here, I think this would be a good answer to choose or to indicate for this particular problem. Now you can do part B on your own. This time the population target is 488 million. And when you try part B on your own, don't just change the calculator to 488. I would suggest working through the entire problem again, just to make sure that you've got the technique down and that you can reproduce this on your own. Let's finish out the video with this particular example here, the value of a car. The Chevy Cobalt that is t years old is modeled by this equation. The value based on time is equal to this. By the way, remember the names that we gave the exponential equations. This first number is what we call the initial value. So in other words, this car was worth $16,500 initially. And we call this value our growth or decay rate. Now, one thing I want to point out is that this rate is always relative to the number 1. If it's bigger than 1, then the exponential function is growing. If it's smaller than 1, then it's decaying. And since 0.812 is 0.18 less than 1, then we would say that this has a rate of decay of 18%. So 18% per year is what the value of this car is losing. Now we can use an exponential or logarithmic equation to answer A, B, or C. I'm going to work on part B. Let's say we would like to sell this car when it's worth $4,000. How long can I own this vehicle, or how long should I own this vehicle before I decide to sell it? Well, I think the process for this is going to be very much the same as the last example. So following our setup here, I'd like for you to try to solve this on your own. Please pause the video now and resume playback in a moment to check your work. And with this approach, I first divided both sides by 16,500 and had that equal to some base to the power of t. Since I'm looking for t, it's really nice to rewrite as an exponential next. So log base 0.82 of 4,000 divided by 16,500 is equal to t. That's when I went to the calculator and obtained the result, 7.1406. So I hope that helps you better understand some of these word problems as well as exponential and logarithmic equations in general. We've got some more word problems to cover in the next video. Thanks for watching.